welcome today. So a couple quick things before we get into the primary content. So housekeeping, today's session will be recorded and it'll be shared via email within 48 hours. We have a resources section on neuralmagic.com that has all of our previous recordings and webinars, as well as some podcasts and other cool things out there. We've also got some technical papers for you to check out, our pruning guide and a ICML paper that our team presented. So that is all there for your perusal. We also feel free to ask questions at any time during the session. I have the Zoom Q&A tab open, so you are welcome to ask a question anytime. And in fact, you can give it a try right now by telling us where you're joining from today. So if you see down in the Zoom toolbar at the bottom, you should see the Q&A tab. So I encourage you to jump in and tell us where you're dialing in from. Oh, wow, we have someone from Rome, Italy. We have Matt from Boston. Hey, Matt. Yeah. Participating. So I think Rome, Italy, and our Sasha's is represented as well. So excellent, thank you. All right, and I lost my Zoom for a second there. So now we don't know what happens. I think, Sasha, I'm in as a participant. So if you could make me, let's see if I can present. Boom, share. Garb, can you see my screen?
I can see your screen, and we've got a couple more people from, let's see, Atlanta, Lithuania, and Ireland.
Awesome.
Pretty awesome. Yes.
Excellent. Well, all right, so we're back. That happens every once in a while with Zoom. We just roll with it. So we'll jump in here. Thank you, everyone, for joining today's session, No Hardware AI. We're going to talk about Neural Magic and what we do and how we deliver deep learning performance with software flexibility. So my name is Brian House. I'm the Chief Commercial Officer here. So I manage a number of our teams as we build a product and bring it to market. I'm joined by my colleague, Gaurav.
Hi, everyone. Gaurav Rao, Head of Product. So everything with product management and product strategy. Look forward to talking with you all today.
Awesome. Thanks, Gaurav. So let's, without further ado, let's jump in and tell you a little bit about the Neural Magic story. So Neural Magic is a early stage software company that was a spin out of MIT. It was founded by Professor Nir Shavit and one of his longtime students and colleagues, Dr. Alex Matveev. Nir and Alex, their background is in high performance computing. And in fact, Nir wrote the textbook on multi-core programming. So for those of you that study parallel algorithms and high performance computing, I'm sure you've read that textbook. And we've got a very technical team, lots of engineers, we've got great investors, and we've built a team of software development individuals and go-to-market folks who come from the enterprise software space. So we know how to build and deliver enterprise software for organizations as part of their mission critical infrastructure. And so the origin story for Neural Magic is really interesting. So Nir's background in high performance computing, started working in computational neurobiology, as one does, and specifically working on a project between MIT and Harvard on mapping the connectome, all the neural pathways and synapses in the brain, to understand better how the brain works. And so this was an interesting challenge with which they were using deep learning, specifically segmentation models, to map all the tissue cells in the brain tissue. Specifically, what they do is they take a cubic millimeter of brain tissue, which is the size of a grain of salt. Turns out that's 2 petabytes of information, and it's coming off an electron microscope at about a terabyte an hour. So it's like 30,000 slices of this tiny little piece of brain tissue, and then they're mapping all the connections within that, similar to like the Human Genome Project. Suffice to say, that was a tremendous amount of information, and it was coming off very quickly off the microscope. And so if they wanted to apply traditional deep learning deployment techniques, utilizing GPUs to process all of this, they need a large cluster of GPUs. And frankly, it was way too much information to round trip to the cloud, coming out at a terabyte an hour off the microscope. And so they didn't have a large cluster of GPUs, and they certainly weren't going to send it to the cloud. And so it created an opportunity to step back and say, is there a different way to attack this computational challenge? And so they sort of rethought how neural networks were executed, and said, applied their understanding of multi-core programming and how CPUs work at a very low level. And that sort of became the technical foundation, if you will, of neural magic. And I'll talk a little bit about the insights they gathered in that process that become the foundations of our product in our session today. So that's our origin story. And they said, hey, this sounds like a lot bigger than computational neurobiology. Maybe there's something more here. And they quickly went and raised money and formed a company. And so that's how we got to where we are today. So there's 3 fundamental challenges that neural magic is designed to solve. And we sort of refer to this all in this category of no hardware AI. So the first is, as I mentioned in the Connect Home project, typically we rely on specialized hardware to train models, specialized hardware to run inference, depending on the types of models and the performance and throughput requirements. And those models, that specialized hardware is expensive. It's hard to acquire. It's not available in all the places we need it, whether that be at the edge or on location. It's not oftentimes not available in your data center, and sometimes not even in the cloud cost effectively. The second problem is that oftentimes when you have specialized hardware, now suddenly everything needs to be, all your software deployment processes need to be hardware aware. So it adds tremendous complexity into the software deployment pipeline as you're building applications that include deep learning models as part of that application experience. And so it adds all sorts of complexity, both in the data center management piece for the IT and DevOps teams, but as well as for the application development and data science teams, and building that whole pipeline from end to end. And then lastly, as we saw very real in the Connectomics example, is they're memory limited. So when, GPUs typically have something like 16 gigabytes of memory. When you have data coming off at a terabyte an hour, you're going to need a whole bunch of those. It's a massive amount of data. And so there's lots of other ways that this sort of memory limitation comes into play. It means people shrink models to fit into deployment footprints or training footprints. When you ask someone how much data, how big their model and data set is that they train on, if they have a 16 gig GPU, they typically are 15.5 gigs, right? And if we want to start to do deep learning on things like cell tissue, digital pathology, satellite images, high-res video, we often spend a lot of time shrinking the information down to fit into the memory constraints of the hardware accelerator. And so these are the 3 problems that ultimately the company was designed to solve: eliminate the need for specialized hardware, reduce complexity in deployment pipelines, and sort of step away from this memory limitation that these hardware accelerators always impose. And so that is really behind the AI software runtime that we've built here at Neural Magic. What it does, it allows you to use flexible, abundant CPU resources that you have, whether they be on-prem, in the cloud at the edge. You can use any x86 CPU to run this software, nothing special required. 2, because it's simply software, you can simplify your CI/CD pipelines. You don't need hardware-aware processes. You're not rewriting everything. You can take advantage of virtualization, containers, all the tools that you utilize to deploy at scale. For other applications, you can now apply for deep learning applications. And finally, because we don't have the memory limitations, the CPU comes out of the box with almost an order of magnitude more memory than a GPU. You can have bigger inputs. You can have multiple models in a pipeline, all in a single CPU device. And as we grow into the training side of the house, today we're inference only, it means you can actually train bigger, more accurate models because you're not limited to the size constraints. You don't have to do hard distributed training and setups in order to train bigger models, which is where we see the future of deep learning going. So 3 problems that we set out to address, and we provide solutions for each with our software. And then with that, you get great performance. On average, we provide about 3 to 4x performance gain compared to other CPU options. This always is model and data dependent, but what you see when we aggregate across a large number of models, we get great performance. And what that means is that it drives down your cost per inference, particularly your cost per inference at scale. So there's significant cost savings available if you can deploy on CPUs and deploy at CPUs in high performance settings, right? Today, many models are deployed on CPUs, but when they are, they come at a cost. There's a trade-off. I have to give up latency. I have to give up model accuracy. I have to make changes. And so we eliminate those trade-offs. You get all the benefits of the flexibility and abundance of CPUs with none of the performance hits. And that's really at the heart of what our value proposition is. Now, often what we get at this point is, well, how does all this work? Either that or I don't believe you. And so this goes back to the insights that Nir and Alex had during their work at MIT in the Connectomics project. And so there's 2 sort of critical insights they gained when they were looking at deep learning performance and how we could change the game and rethink the problem, this sort of computational challenge that was a neural network. So the first is this idea of sparse acceleration. And so their insight was there's a sparse algorithm hidden in every neural network. But because the hammer we use to address this computational problem is just lots and lots of flops, typically what happens is we brute force our way through it, and we just saturate the cores, throw a whole bunch of compute at it, and power through that model. But what Nir and Alex realized is that actually you can dramatically decrease the amount of compute required and do so without sacrificing accuracy. And so what we can do is use techniques like pruning and quantization to compress the model. And we'll show you how we do that with some of the tools, but also we have algorithms that accelerate sparse computation. So they're designed to get performance benefits from this sparse computation, right? So there's lots of tools out there to prune models to shrink their size because you want to deploy them on a mobile phone or on an IoT device or an embedded system. But what you see with existing solutions in the markets, none of those get faster, they just get smaller. What we do uniquely is the ability to accelerate the performance of that model in addition to compressing it. So that's the first foundation. The second foundation is this idea of memory acceleration. So one of the things that we've learned over time is that compute alone is not enough to solve the performance challenges associated with deep learning applications. And every model architecture, be it ResNets or MobileNets or faster RCNNs or YOLOs or what have you, have a combination of compute-bound and memory-bound parts of that model. And those are different on a model-by-model basis. Now, we can throw flops at this and accelerate the compute-bound piece, and that's typically what hardware accelerators do, but they're still memory-bound. And we know this because simply adding flops doesn't add to a linear increase in performance on those models, because other parts of the models are memory bound. So you need to figure out a way to accelerate that piece too. And so this is where our background in multi-core programming comes in. We understand how to accelerate the memory bound pieces of those models. We take advantage of the large cache sizes and the unique architecture in the CPU to minimize data movement and accelerate those memory bound pieces. So these are all, again, algorithms that are in our inference engine. Suffice to say, it's the combination of these two, sparse accelerations and memory acceleration, is how we generate great unprecedented performance for CPUs and allow you to take advantage of this abundant resource that might be in your reserve fleet in the cloud, might be on your desktop workstation sitting underneath your where you sit every day. So lots of interesting pieces here. And what, the net of it is we reduce the amount of compute, get speed from that, but also make the model more memory bound and accelerate the memory bound components and get performance from that. And that's how we get performance overall. So where can you use Neural Magic today? As I mentioned, we have an inference solution. We started with inference to bring a product to market fast. We have a vision to go to training, but you are available to use it today for inference and do so specifically on computer vision use cases. So we support image classification and object detection. And our value proposition is software flexibility that enables you to lower costs and deploy models either to replace GPUs that might already be there or to accelerate the ones that you have on CPUs, or to deploy models in new places that you just don't have the ability to deploy them today. So you'll see more in the demo, but we have lots of models in our model repo and we support things like ResNets, mobile nets, Inception, efficient nets, SSDs. We're adding YOLO in a few weeks, so really excited about that as well. And that actually gets us to the interactive component of today's session. So we have a poll, and so I'm going to see if I can figure out how to do a poll. So I have a poll question. The question is, what models do you use today, whether it be in research or in production? I'd love to get a sense of types of models people are utilizing. So I know you got to find the Zoom window and come back. So I encourage you to come in and do it. All right, we've got starting to get responses. Excellent. All right, almost half of the people here today have given us response. Let's see, I'll give it another 10 seconds here to see if we've got a couple more responses in this. Oh, there's 1, 2, 3, excellent. See. All right, well, that's good. So this is great. Leader in the house is ResNet, 10 of the 13 responses. And YOLO is number 2. 54% of users use YOLO v3. So that's great to see with mobile nets, efficient nets, SSDs all coming in. So thank you for that. All right, so I'll close that. So next up, I'm going to talk a little bit about the personas and where our software fits into your deep learning workflow. And so there's 2 primary personas that we engage and interact with our software. So the first is the data scientist, and this is in the development of their model to ensure that it meets business objectives and in terms of both performance and accuracy. And then we have the machine learning engineer who's responsible for deploying this and from a DevOps perspective at scale. So for the data scientist, there's 2 primary components of our technology. So the first is we have a model repo. So we take open source models that you find in the TensorFlow Zoo or the PyTorch Zoo, and we pre-train and optimize those to take advantage of the algorithms I described in the Neural Magic Inference engine. So those are ready to use. You can transfer learn on your data and you're off and running. So get started fast. Alternatively, most customers that we've talked to have models in their own private model repo. And they're typically sort of slight tweaks or variations on open source models. And so we have a set of tools that we can provide you to allow you to do the same optimizations that we do on the models. We're really excited about some of the tools here. So we have a capability called neuralmagicML, which is a set of APIs to do it. And then we're building, getting close to release a new product called Sparsify, which provides an interface on top of this, allows you to prune models and really see what the performance optimization gains can be in addition to the compression gains for those models. So those are all available, and this is for the data scientists. They work right in TensorFlow and PyTorch, and they're ready for you to use. And the output of all of this is a representation of your model in the format of an Onyx file. So we take Onyx files and we run those. So let's say you have a private model, you go and prune it, and you see you're going to get 3-4x better performance as a result of that. You go through a retraining process similar to what you do for quantization. Then you're ready to deploy your model into production. That's when you go to the ML engineer. Maybe that this is you and you do both these roles. Maybe this is one of your counterparts who's deploying models for you on the DevOps side. So with this, we have our inference engine that sits very neatly into a typical deployment architecture. So it's just a library that you call. It sits right within your model serving solution. We deliver a model serving solution if you don't have one. So it's just based on the Onyx runtime server. And you can deploy us in the same way you deploy any applications. People deploy their application in Docker and install us right there. They manage those Docker containers with Kubernetes and orchestrate that as they scale up and scale down. You can install on bare metal or on virtual machines. So really very flexible and easy to fit into your deployment architecture. And you just simply spill code and point with a couple lines of software of code to point it to the inference engine to actually process the request, feed it data, and deliver back a prediction. We'll see this in the demo. Gar will show that. Cool. So let's go a little bit further to give you a sense of what you see in the model repo. So we have lots of models for both classification and detection. This is an area that's growing all the time. And as I mentioned, this is about faster time to value, right? It gets you a model, you're up and running, delivers the results you need, and then you can get out to deploy. So it's sort of to think of it as an advanced starting point for your applications. And what we do is we give you a dense or base version, then we have a sort of a full accuracy version, then a performance version we call RecalPerf, which sacrifices 1 point in accuracy, but gives you about 20-25% better performance. And so you'll see lots of models in our repo where you can balance the line between performance and accuracy to meet your application requirements. Next up is pruning. We'll see a notebook version of this, but what you see here is a screenshot from a product that we're building called Sparsify. And so what this is an easy to use user experience that gives you really great insights into where the computational bottlenecks are within your model and how you can prune them and preserve accuracy with that. And so you can see that all right in there, and you can and tweak to your heart's content. What we're building actually is a one-shot pruning. So what we can do is you put your model in, we do an analysis of it, we tell you what the benchmarking potential is, or the performance gain potential is, the compression gain potential, and then we do a one-shot prune. Then you can go and tweak the knobs yourself on a layer-by-layer basis, and then quickly that export go retraining pipeline, run a retrain real quick, and then you're off to the races and ready to deploy a model. So very easy. This is something that's coming out later this year, and so we're going to have a public and private betas. So if you're interested in you're doing pruning today, that would be we'd love to have you in our beta program. And that leads me to my second poll. So we have another poll. I got to pull it up here. So give me what optimizations are you employing today specifically to get models into production. So things like quantization, structured pruning, unstructured pruning. Always interesting to see how people are doing optimizations today. One of the things that's interesting while you guys are answering the question is with Sparsify, you actually can use it simply for compression gains, right? So if you're pruning models to deploy for IoT devices, as an example, you can use Sparsify to prune it, get the optimal prune and accuracy benchmark, and then take that model and deploy it into a edge deployment on a small device, so strictly for compression. Second piece of it is we actually then allow you to see what performance gain you get if you ran it with the sparse acceleration algorithms in the neuralmagic engine, but you don't actually have to do that. So lots of really interesting options there. And the results here, we see 78% of people are not doing optimizations. It's almost 80%. We see a couple doing quantization and just a few doing pruning. So interestingly, this is very much in keeping with what we've seen in practice. And this is, we think, is a tremendous opportunity. If you look at the research coming out of places like NeurIPS and ICML and TinyML, you see there's, all the research is very much focused on sparsity as a performance acceleration, but it's the transition into production yet is still early. And so this is part of why we're releasing, building Sparsify, is to help people take advantage of these techniques to drive performance. Lastly, we have the inference engine. And all I'm going to say on this slide, because we're going to see this in the demo here in just a minute, is that on any x86 CPU that has AVX instructions, be it AVX2 or AVX512, you can run our inference engine and get great deep learning performance on your CPU. There's a lot more here that Gaurav's going to share, so I don't want to steal his thunder, but give you a sense of that. And then just to give you a sense of what we see, just a couple model examples. This is MobileNet V2 SSD, batch size 1, running on a 4-core machine. You have a 4x increase in images as compared to OpenVINO and 70% reduction in costs, right? So this is an environment with just a really tiny CPU, runs at 34 cents an hour on demand. You can get great performance and drive your cost of inference down significantly as a result of that performance. Another example is this is ResNet 50. This is our Recal Perf version. 3x better performance at batch size 64 with a more than 50% reduction in cost. This is all running at FP32. We see similar numbers when comparing against GPU options. So MobileNet V2 SSD compared to a T4 GPU. Again, great performance, much more cost effective. So it gives you a sense of some of the things that we're seeing in our testing, and we're building software. We have it available. So if you want to try this in your own environment, we can do that as well. So with that, I'm going to pause and I'm going to pass control over to my colleague Gaurav so you can show your demo. Are you ready, Gaurav?
I am ready.
Awesome. And then I'll let you take it away.
How does that look? Can everyone see the screen?
Yep, I can see it. It looks good.
Perfect. All right, so I'm going to show you guys 2 demos in the flavor of Jupyter Notebooks, and they're going to build on from what Brian had described earlier. So if you recall in one of the earlier slides, we had an insight slide, and specifically, there were 2 key insights that were helping us drive performance on CPUs. One was sort of sparse acceleration, and 2 was memory acceleration. So, in these 2 notebooks, what you're going to see is sort of an encapsulation of both of those, right? And through the demo, you're going to encounter our model repo, the neuralmagicML tooling or toolkit, as well as the inferencing engine. So I like to set the context before we kind of walk through it. And the first notebook is going to actually show you how we create sort of pruned or sparse models, right? Taking advantage of the natural sparsity within a network. And then we're going to export that model and then run it in the engine, which is going to be the second set of notebooks. So, if you think back visually to Brian's slides, there was the data scientist slide that's kind of either starting with a known model or kind of going through our ML toolkit and generating a graph output. And then the second slide was, once you have that graph output, actually compiling and executing an inference in the NeuralMagic inferencing engine. And that's actually exactly what we're going to see. So in this first notebook, you'll see that this is a demo example of pruning with the Atom Optimizer. We happen to pick SDG here, but it happens to be for PyTorch. And one of the first things I'll call out here is, in Brian's slide, you'd notice that there was a larger bubble around frameworks. So all of the ML tooling, our pruning, transfer learning, so effectively everything that's used to compress or optimize a model is actually framework dependent, right? So we can support PyTorch, TensorFlow, ONNX, and we're continuing to add more and more support, like for Keras in the future. So this specific one is an example of pruning with NeuralMagic in the context of a PyTorch environment with Atom Optimizer. So, what we're going to walk through is, how do we set it up? Simply, how easy is it to install? We'll take a look at a sample network. I believe it's a simple CNN with MNIST data sets. And then we're going to show you sort of the implementation of the pruning algorithms, right, and the techniques that we use to employ to get speed up via pruning. And then we'll go through a hyperparameter sort of setting, as well as recalibration. Now, I'm not actually going to run the recalibration here, but for demo purposes, I'll show you what the output looks like for sake of time, and then we'll go into the inferencing engine. So, just a little bit of background. I won't spend a lot of time here, but, what we use in NeuralMagic is an unstructured pruning technique. So effectively, what we're doing is we look at the network and understand where there are extra or over parameterization happening, right? And we see over parameterization happening frequently within, I'd say, computer vision networks. And, our job or the tool's job, is to figure out where we have too many parameters, and effectively, how do we set those weights to zero, right? So the pruning or the cutting here is actually by assigning weights or over parameters to zero, and then intelligently skipping those weights in the inferencing engine, right? So this was kind of Brian's point earlier. It's not just about the pruning, right, or the compression, but it's actually running right at runtime or process time, the ability to skip those and compile for performance. So just a little bit of background on what we're actually doing from a pruning standpoint. So, step one is actually setting up our environment. And, Brian kind of mentioned a few different product sets, like the ML Toolkit inferencing engine as an example. And, we like to show that the way to install is just a simple pip install command, right? So to run the ML tooling, we pip install neuralmagicML. So I'm going to go ahead and execute that cell. And you can see that it's been set up and installed for my notebook. And then the second step here, before we actually start looking at how to prune, we're going to actually just show you the network that we're pruning here. So it's a very, very simple CNN. I believe, if I remember, it's a 5-layer network, but we're going to actually visualize it here, so you'll be able to see it. So this has come back. So it's an MNIST data set, right? And we provide both the training data set and the validation data set. But you can see here, the blocks, right? So we have 5 layers, including a classifier at the end. And we tell you exactly what the training data set looks like and what the validation data set looks like, specifically the number of data points and sort of how we're normalizing it. Now comes the, I'd say, the algorithm or the model analysis. So, Brian mentioned a point earlier that, pruning or compression can be interesting for performance, but the trade-off is usually accuracy. So what we're doing here is we are actually identifying and analyzing the layers within the network and determining which one of these are actually best suited for pruning, right? Or in our case, best suited for assigning weights to 0. So what we do first is run a sensitivity analysis. And when I ran the sensitivity analysis on this simple CNN, it's come back and it's shown me there are a few layers, specifically block 0, that are fairly sensitive. And then it's also showing me that blocks 1, 2, and 3 are less sensitive, right? And this is correlating to the number of parameters that are within these layers that we feel can be either pruned or we don't want to be touching at all, right? So the next step that we typically go through is once we've identified how sensitive each layer is, we make a recommendation, right? Based on that layer and that model analysis on exactly how much to prune, right? And as I mentioned before, pruning here is effectively setting the weights to 0. So what percentage of the weights within each layer are we actually setting to 0? And, we create a very simple, I would say, visualization to show this in the notebook. And, as it was introduced earlier, we have a new product coming out soon called Sparsify, where a lot more of this is going to be UI UX driven, and more, I would say, automated and self-service. So not necessarily CLI or command or notebook driven. So, the results came back. And if you remember, I had 5 layers and there were a few sensitive layers, specifically block 0 and block, the classifier block at the end. And then we had a few that were not as sensitive. So it's not shocking to see that our tooling is actually recommending not to prune that first block at all, or block 0, because we saw it was fairly sensitive. So here we've set the desired sparsity to 0.25. And anything effectively below 0.6 from our tooling standpoint is not going to do any, we would say, pruning of that layer. And then you can see here that in blocks 1 and block 2, we are applying an 80% and 90% desired sparsity, right? So for these 2 layers, for layer 1, we're saying 80% of the weights are being set to 0. And in block 2, we're saying 90% of the weights are being set to 0. And that's because we've determined that the loss sensitivity is fairly low. And then similarly for block 3, because of the low sensitivity, we're assigning 90% sparsity. And of course, you can be more aggressive here, right? You can set this to 0.92, 0.93. And all of this depends on the level of trade-off you want to make with accuracy. And what I like to point out with this last one is, if you remembered, it was highly sensitive, but we're still pruning. And this is sort of an intelligence factor that the tooling has come out with, which is, because the features are linear, we're actually still pruning, because we believe that we can still set the weights to 0 for this specific layer and not impact accuracy while still improving performance. So there's even more, I would say, granular level model analysis in terms of not just the layer, but sort of the types of operators that are running within that layer, where we are still making a recommendation on. So the takeaway on that layer was, even though it was sensitive, we still feel that the types of operators being used within that layer are prunable. So we're going to go ahead and prune them. So that is sort of the config file that gets set up, and that effectively would go back into your retraining process. So rather than go through the retraining itself for time, I am going to show you how easy it is to sort of integrate this back into your existing training environment. So I mentioned earlier that this is a PyTorch notebook. So the first things that you're going to start to see here is, once I export or create this config file, we want to include all of the relevant code to simply plug back this config file into your existing sort of PyTorch, I'd say, training environment, right? So for anyone that's been building and training in PyTorch, I would hope that some of the commands that you're starting to see here in terms of how we're loading the data, how we apply the loss sensitivity, make sense, right? Because these would be the same commands that you would be running in I would say, most normal PyTorch training settings. And of course, this can all be modified. So the final step in the notebook here would then to actually be to export the config file in this Onyx, run this back into your existing training flow, and then we would sort of run and test for performance. So keep this in mind, because now we're going to jump to, we've taken a simple model, we've pruned it, we've created a config, and now we have sort of an export. Now I'm going to show you in the next notebook how you actually take an export, right, specifically in Onyx, and then run it in our engine. So if I click over here, I have another demo. And this notebook is going to show you, like I said, how do we actually run and compile within neuralmagic and generate an inference. And the first things that you're going to start to see is we do something similar in terms of setting up the environment, but very quickly we import our Onyx, right? So for the neuralmagic inferencing engine, we take Onyx as our input, which is why that last notebook, the last step was export to Onyx, right? Because that's sort of the input we take into the engine. And we can convert either TensorFlow, PyTorch natively into an Onyx representation cleanly, without loss, and then we'd run that for inference in the engine. So similar to the prior notebook, the first steps that we're going to do here are pip install and sort of, get our environment set up. So again, I'm running this live here. So you're going to see, actually in my case, that I'm going to uninstall everything that I have and reinstall it. It's warning me that I need to update some of my tooling, but let's see, yep, get higher pip install version. Okay, so I've successfully installed. So the next step is actually fairly standard. We're going to import our packages. Hopefully none of this is too crazy. And then now what we're going to do is we're going to select a model. So, Brian mentioned earlier a couple of key things: the tooling, the inference engine, but a model repo. And for the sake of this demo, we're going to actually visualize, right, a part of our model repo here, so you can see it. And these are, as he mentioned, pre-trained, performance-optimized networks that we've trained either from ImageNet in the case of image classification, or COCO, right, in the case of object detection. And these are a number of different networks you can kind of see here in the demo. This one happens to be, CV classification, so it's going to be ImageNet. But you can just see some of the models that we have, like Inception v3, MobileNet v1, MobileNet v2, ResNets, VGGs, and so forth. And what's more interesting is we have different flavors. So I'll pick ResNet 50 since the poll that you guys took, a lot of people have been working with ResNet 50. And I'll pick TensorFlow, just you see a lot of people typically training in TensorFlow. But these three were what I wanted to call out. So in the repo, we offer different, I would say, flavors of networks that you can run off the shelf, right? So base means it's effectively what you would get from Torch Vision or TensorFlow Lite repo that we've downloaded and put into our engine. So no compression and no, I would say, model optimization techniques applied. On the compute standpoint, it would be all memory acceleration in our engine. And then we have a recal version of the model. And recal is where we've pruned, right? So we kind of just walk through the pruning notebook, that process in favor of performance without dropping any baseline or top one accuracy. And then the third flavor of the model, in this case, ResNet 50, is a recal perf model, which is going through that same pruning notebook process that we went through, but this time favoring performance at the cost of 1% of baseline accuracy or top one accuracy. So I'll show this one. Let's do ResNet 50, ImageNet, TensorFlow, recal perf, right? So these are going to be our most performant models in the repo. And the next step from my model repo is download that model, right? And then we'll prepare it for inference. So I'm going to go ahead and download that ResNet 50. So you can see I've downloaded CV classification, ResNet V1, 50, recalperf. And the next step is, I would say the step that shows us how we're actually compiling, right? And how you actually run an inference. And it actually comes down to one command. So it's neuralmagic _ model equals neuralmagic create model. And it takes 3 arguments: the model file path, right? So in this case, this long file path to my Onyx model. It takes the batch size, and it takes the number of cores that you're going to run on. So with those 3 arguments, that's what neuralmagic, our sort of Python API, takes in as arguments to compile and run an inference. So for this demo, I'm going to run that, and you're going to see sort of some information coming back again on, my specific environment. So again, it has found the file path. I've put batch size 1 because what we're going to do here is we're going to prepare the model for compilation, and we're actually going to run an inference and validate the accuracy of the output, and then we're going to go through a benchmark. So for the accuracy, I'm just going to run batch size 1. And this is actually running on a C5 2XL from Amazon, or a 4-core, a 4 physical core instance, which is why it's detected I have 4 cores. And this happens to be a single socket, and it has AVX512, which is the CPU instructions that we take advantage of within the processor to gain speed. So now and this is actually, so the model is actually compiled. So right now, the next step here is we actually provide a little bit of code. Of course, this is anything someone can modify themselves, but we're going to actually run an inference. And we're going to take a random image from ImageNet and classify it and see how close we are. And this is completely at random. So this happens to be a boa constrictor, and I would argue someone crazy who would put a boa constrictor around their neck. I am not one of those people, but with the model here has returned the classes, right? So it's come back with boa constrictor as number 1, rock python, night snake, and king snake, and hognose snake. So, we've compiled, we've created an inference, and now we're just sort of very quickly checking how well the model has done in terms of classifying. So that was sort of the first part of the demo, is just kind of getting you familiar with how you import, how you install simply through pip install, the neuralmagic create command, which is necessary for compiling and executing. And it's effectively taking advantage of the Python API we have around our inferencing engine. And now, this is where things get a little bit more interesting. We ship flavors of notebooks to our end users, and this is where you can sort of customize and effectively see performance within your own environment. So think of this as now the benchmarking part of the demo. So the first thing I can do is actually select the number of cores I'd like to benchmark against. And because this is a 4-core AWS instance, I have 2 cores or 4 cores to choose from. So for this, I'm going to choose 4-core to start. I'm going to next be asked to select my batch size. I will show real time. So let's do batch size 1, and just looking at the time, for sake of time, I'll do batch size 8. So you guys get a little bit sense of throughput here too. And then the next set of code is actually the benchmarking script, which is something our users can also modify. So you can change the number of iterations, the number of warm-up iterations, but for this demo, we run 100 iterations with about 20 warm-up iterations. And you can sort of see the same set of arguments that are being passed through from earlier, right? The number of cores, the file path, and the batch size. So I'm going to go ahead and run that. And now we're actually running a benchmark. So you'll see 2 sets of benchmarks being processed, and then we've created a neat little visualization so that you're not staring at command prompts and trying to parse out what the milliseconds and sort of inference times look like. So that just completed. Let's look at our model execution times. So if you remember, This was a ResNet 50 classification network, and we're running our recal perf model, which is, performance within 1% of top one or baseline accuracy. So on 4 cores, batch size 8, we're seeing about 114 images or items per second with an average image time of about 8.73 milliseconds per batch, right? With a total batch time of about, let's call it 70 milliseconds. And then on the 4 core batch size 1, we're seeing roughly 100 items or images per second with an average image time of 9.99 milliseconds. So that completes the demo. And just to kind of recap again, this was kind of showing you how we create some of these prune models that you ultimately will see in our model repo by going through that pruning notebook and exercise. And then once you have that, how do we actually run an inference in our engine, and what does performance look like? So based on that, why don't I give control back to Brian and see if there's any questions.
Awesome, Garth. Thank you so much for the excellent demo there. Very good, as usual. So I'm going to pull up my slides and just do a quick wrap up. And then this is a great proxy to request folks to ask questions. I think we've seen a few that we'll review in there. But before we do that, so as we saw today, we're giving you tremendous deep learning performance running on everyday commodity CPUs, but all the flexibility of software. So what that means is, this solution can fit seamlessly on existing software deployment pipelines. So it makes it really easy to move to deployment without having to do lots of special actions to support specialized hardware. And because it's software, we can adapt very rapidly to support latest models, algorithms, research, right? So, there's no need to swap out the hardware to take advantage of some new capability or some new advance in the market, deep learning market, which is moving incredibly quickly. So we have all the benefits to respond and move rapidly because we're a software-only solution. You can deploy an abundant CPU resources, as we mentioned, on-prem, in the cloud, at the edge, and all of this is to help you reduce and lower your costs for deep learning deployments at scale. Lower the IRR to get your deployment, your application out, and then reduce that cost as that application grows and scales. So with that, I'm going to open it up for questions. While folks are putting questions in, you can check out our resources page. That's where we publish our recorded webinars. You also see papers and blog posts and all sorts of other assets, some cool videos too. So I encourage you to check those out. You can request product access at the URL you hear /product-access, or send us an email, learnmore@neuralmagic.com. We're happy to. So let's see some of the questions we have here. So one, says, this looks awesome. Thank you, Ram. And can I get access to this via a pip install? So yes, we actually have a beta program. And we can get that out today, and then we can also we have lots more coming and more products coming for alphas and betas. So we'd love to talk to you specifically. We'll follow up, Ram, around getting you access to the software. Garb, there's a question on benchmarking containers or VMware performance via bare metal. Can you give us some insight on that? That was from Ian.
Yeah, and it was a great question, Ian. It's funny you mention it because we are actively going through a number of different, I would say, benchmarking tests, because we don't anticipate, I would say, drastically different performance depending on the types of environments. And that's specifically because of how we buy into the CPUs and sort of the CPU resources. But we do have, I would say, different sets of numbers, whether you're running on VMs directly in a container or on bare metal. So we didn't show them in the presentation, but happy to follow up if that's of interest.
Well, second question from Ian was around support for Conda installs. So it should work. We haven't tested that specifically, but so there are some issues around in terms of standard packages, but you could do a pip install into a Conda environment and then use that to install, and that will work as well. So that's an option for you. We have a question on, can this be performed on quantized models? What do you want to take that one, Garv?
Sure, and the answer is yes. And I'm glad you asked the question. And I think Ramakrishnan had asked another question about, are we showing FP32 in the demo? And I should have specified the answer to that was yes. So the notebooks show FP32 performance, but the unique insights and algorithms that we have are also being extended to both quantized networks, and then we actually see sort of a compounding effect with sparsity on top of quantized networks, right? So this thought of sparse quantization, which will give us an additional factor, right, in terms of performance.
Excellent. So I see somebody has their hand raised, so you can submit questions via the Q&A tab here, right in Zoom, and we will answer those. But we want to talk a little bit maybe about sort of our upcoming Sparsify beta. Maybe that's want to give a little sneak preview of that.
Yeah, so we've got, as we've been showing, and you saw it in the notebooks. Right now, it's still a command line or a CLI-driven process to prune networks, and we do have a UI-driven self-service tool coming. We should be opening, I would say, the beta process sometime closer in the next, I'd say, 4 weeks or so. Where you'd be able to register. We'd love people, if you're interested to try it out, let us know as soon as possible. And we'd be happy to get you trying sort of the beta version of this product and sort of giving us some feedback as we build this out.
Yeah, excellent. Yeah, so if you're doing any pruning today, that would be a great piece. Or if you're interested in pruning but haven't tried it, that would be another great user persona as we prepare this. And this is, if anyone's going to NeurUps or attending NeurUps in a virtual way this year, this is something that we'll be featuring in our booth at NeurUps, and we actually are doing planning to do a workshop on as well. So encourage you to say hello and check it out. Ram Krishnan also asked if we had thoughts on NLP models. So great question. So we've definitely done investigation into NLP. We've actually run BERT end to end in the engine, and we're excited about NLP because we think our techniques of sparse acceleration and memory acceleration will perform very well, specifically on transformer-based models in the NLP. I think it's a really very compelling fit between the technology and those model architectures. And they're a perfect example of very, very large models that would benefit from the much larger memory capacity on a CPU. But we're a startup, so we have to do everything one step at a time. So our focus today is on computer vision. We anticipate NLP as something second half of next year that we'll be able to do with the product. And it's a conversation Garv and I have all the time. It's how do we do that faster? But if you're interested, we'd love to learn more. So please share. I know we're coming to the top of the hour. He says thank you. I will let everyone go there. As I mentioned, the session today is recorded, so thank you. You can share it with your colleagues or recap the demo and watch it again. But really appreciate your time today. Have a great rest of your day around the world, and hope to see you at a future webinar. Thanks, everyone.